Dear students, in the last class we have seen the solution of the differential equation of a damped harmonic oscillator, and also we discussed the three different cases based on the values of k and omega. In today's class we are going to see the comparison between the time displacement curves in the three cases, then the relaxation time and quality factor of the oscillator. So first of all, let us see the comparison between the time displacement curves in the three cases. So based on the relative values of k and omega, there are three different cases. The first one is if k is greater than omega, that is called over-damped condition or heavy damping. Second one, if k is equal to omega, critical damping. And the third case is under-damped condition, that is if k less than omega, that is also known as light damping. Okay, so if we plot the displacement versus time graph in the case of these three cases, in the first case over-damped condition, it is in that the displacement decreases exponentially with time without performing any oscillation. There is an exponential decrease of amplitude with respect to time, and finally it decreases to 0. Now in critical damping case, there is an exponential decrease of displacement with respect to time, and in critical damping condition this exponential decrease in displacement is much faster than that of over-damped condition. Now we are moving to the third case, that is under-damped condition, where k is less than omega. So in that case, the amplitude of oscillation, we have seen in the solution that the displacement x is equal to a e raised to minus kt sine beta t plus phi. So it is an oscillatory motion. In the other two cases, the motion is non-oscillatory. It is very transparent from this diagram. The motion is non-oscillatory. But in the third case, in the under-damped condition, the amplitude of oscillation there also as a e raised to minus kt, there is an exponential decrease with the time, that decreases with the time, but performing some oscillations. So it is an example for an oscillatory motion. Okay, this is how it is represented. So this is all about the comparison of the time displacement curves in the three cases. Now we are moving to the relaxation time. So first of all, let us see what is the relaxation time of an oscillator. It is the time taken to reduce the total mechanical energy to 1 by eth of its initial value. That is what is called relaxation time. Now the mechanical energy is a constant and it is given by the equation E is equal to half m omega square a square. Okay, where omega is the natural frequency of oscillation or angular velocity and a is the amplitude of oscillation. Now we have this amplitude of the damped oscillator. So in the under-damped condition we have seen that x is equal to a e raised to minus kt sine beta t plus phi. That is an oscillatory motion. So there the amplitude part is nothing but a e raised to minus kt. So here in this mechanical energy equation, we can replace the amplitude term with a e raised to minus kt. That is the amplitude of the damped oscillator. Okay, so this is here a square. So on squaring this, what we are getting? A square e raised to minus kt whole square, that is e raised to minus 2 kt. So I am substituting this value in this equation. E is equal to half m omega square a square. So that becomes E is equal to half m omega square a square e raised to minus 2 kt. Now we are putting the two conditions. The first one is at t is equal to 0. When t is equal to 0, what we have? E is equal to E0. I am denoting that with E suffix 0. Energy at t is equal to 0. Half m omega square a square e raised to 0. minus 2k is a constant. So minus 2k into 0 becomes e raised to 0. E raised to 0 is 0. E raised to 0 is 1. So here we have e is equal to e0 half m omega square a square into 1. If it is x raised to 0, that is equal to 1. Here e raised to 0, again 1. Okay, if it is 2 raised to 0, again that is equal to 1. So here we are applying that property here, and so we have at t is equal to 0, the energy is E0 is equal to half m omega square a square. Okay, so therefore after t seconds, in the general equation, if you are putting this is E0 value. If you are putting this E0 in the general equation, the mechanical energy, total mechanical energy, we can write it as, see this half m omega square a square is nothing but our E0. So E0 into e raised to minus 2kt. So I am writing that energy equation, E is equal to E0 e raised to minus 2kt. Okay. Now we have at t is equal to tau. At t is equal to tau. Tau is nothing but the relaxation time. So relaxation time of an oscillator is the time required to reduce the total mechanical energy to 1 by eth of its initial value. Okay, so here we have E is equal to E0 e raised to minus 2k tau. That is, we are just replacing this t with tau. Tau, where tau is the relaxation time. So from that equation we have E by E0 is equal to what? That is equal to e raised to minus 2k tau. Now, as per definition, after tau seconds, we know that energy becomes 1 by eth of its initial value. So this is the initial energy, E0. So we have E is equal to 1 by E of E0, or E by E0 is equal to 1 by E. Now look at these two equations, equations 1 and 2. In the first equation we have E by E0 is equal to e raised to minus 2k tau, where tau is the relaxation time. And in the second equation we have, from the definition of the relaxation time, E by E0 is equal to 1 by E. So let's just say we can equate the two equations, and after equating we have 1 by E is equal to 1 by E. We can write it as e raised to minus 1. That is nothing but that is equal to e raised to minus 2k tau. So we can equate the exponential terms on the exponentials, that is minus 2k tau is equal to minus 1, or 2k tau is equal to 1, that is tau is equal to 1 by 2k. So we have the relaxation time is equal to 1 by 2k, where k is the damping constant. Now therefore we have E is equal to E0 e raised to minus 2kt, and that is equal to this 2k is tau is equal to 1 by 2k. So 2k is 1 by tau. So we can write it as the total mechanical energy E in terms of relaxation time as E is equal to E0 e raised to minus t by tau. Okay, these equations are important as problems will ask from this section. Now I am going to discuss the quality factor of an oscillator. Quality factor is a very important term, and we can define it as 2 pi times the energy stored in the oscillator to the energy loss per cycle. It is defined as the ratio of 2 pi times the energy stored in the oscillator to the energy loss per cycle. Okay. So here we have the mechanical energy of the oscillator, harmonic oscillator, as E is equal to E0 e raised to minus 2kt. That we know how we are getting from in the derivation of relaxation time. We discussed this part. Okay. So we have where E0 is equal to half m omega square a square is the initial energy. Now E is equal to E0 e raised to minus 2kt is the mechanical energy of the oscillator. Now I am finding out the rate of change of energy, that is dE by dt. So take the derivative of energy E with respect to t. So dE by dt is equal to E0 into minus 2k e raised to minus 2kt. So we are writing it as dE by dt is equal to minus 2k E0 e raised to minus 2kt. Okay, now the next line is very important. So I am writing in the next line the rate of loss of energy. Here we have written rate of change of energy with respect to time, and that is dE by dt is equal to minus 2k E0 e raised to minus 2kt. While we are writing it as the rate of loss of energy means there is a decrease in energy. So I am writing it as a positive parameter, that negative comes in that term itself. So we are writing it as the loss of energy, some value p is equal to, some constant p is equal to dE by dt is equal to 2k E0 e raised to minus 2kt. That is the rate of loss of energy. So energy loss per second. Energy loss per second is 2k E. E0 e raised to minus 2kt is nothing but the total energy E. That is per second. So energy loss per cycle. T is the time period to complete one oscillation or one cycle. So we have 2k E into T. Okay. Now what is quality factor? 2 pi times the energy stored in the oscillator divided by energy loss per cycle. So energy stored in the oscillator is capital E divided by energy loss per cycle is 2k E T. E and E gets cancelled. 2 and 2 gets cancelled. So finally what we are getting is quality factor is equal to pi by kt, where T is the time period. So we have capital T is equal to, time period is equal to 2 pi by beta, and we have tau is equal to 1 by 2k, that we know. Tau is equal to 1 by 2k. Okay. So if I am substituting these parameters, what we are getting is, in this, if I am writing it as in terms of tau, we will get it as what? Quality factor Q is equal to beta tau. Okay, see, divide this equation as dividing and multiplying this with 2, then what we have, quality factor Q is equal to 2 pi divided by 2k into T. 2 pi by T is nothing but beta. So this becomes beta. Then tau is 1 by 2k. 1 by 2k is tau. So we can write the quality factor equation as Q is equal to beta tau. Now, okay, if Q is very large, if K is small, if K is the damping coefficient and it is directly related with the damping constant. So if K is small, Q will be large. When damping is small, that's the meaning. And so the quality factor represents nothing but it represents the efficiency of the oscillator. So what does it mean? Quality factor is very high means the oscillator the oscillations of the oscillator dies out very slowly. Okay, the rate of loss of energy becomes very slow. The oscillations of the oscillator dies out slowly if the damping is small or quality factor is high. So directly it's a factor that is related with the efficiency of the oscillator. Okay, so definition is quality factor, we can define it as the ratio of 2 pi times the energy stored in the oscillator to the energy loss per cycle. And we have the equation Q is equal to beta tau. We know that beta is what? Square root of omega square minus k square, where k is the damping coefficient and omega is the natural frequency of oscillation. So if damping coefficient or constant is very small, damping is very small, in that case beta is equivalent to omega. Then we can write this equation as Q is equivalent to omega tau. So this is all about the quality factor. It's a factor that represents the efficiency of the oscillator, and if the quality factor is high means the oscillations will die out very slowly. Okay. So this is all about quality factor, relaxation time, and the comparison between the overdamped, underdamped and critically damped cases. So we will continue in the next class. Till that time, stay home, stay safe. Thank you.